Hello everyone. So today we are going to learn about a new technique to approach problems in math Olympiads. It is called as isogonal conjugates. So this has a lot of applications in various theorems, and we are going to learn it using Ceva's theorem and the area ratios. So let's go step by step and we will finally land in the isogonal conjugates. So let's get started. So let's first see what is Ceva's theorem. This is very helpful in learning isogonal conjugates. Ceva's theorem talks about line segments from the three vertices of the triangle to their respective opposite side. And these line segments that connect vertex of the triangle to its opposite side is called as a CVN. So we have ACVN, AD, BCVN, BE, and CCVN, BF. Now, Ceva's theorem gives us the condition for which these three CVNs concur. Concur means they all pass through a point on the plane. So the condition goes as follows: BD by CD times CE by A times AF by BF equals 1. So it's just determined by points on these three sides. So if they satisfy these conditions, then the CVNs that connect from the vertex opposite to it will all concur at a point. We are not going to get into the proof of this, but we are using the result of Ceva's theorem in order to understand isogonal conjugate points. And together with this in Ceva's theorem, we also have that points out of points DEF, exactly odd number of points must be inside the sides. So you may think that the points DEF may as well lie outside the lines determined by the sides BCCA. But perhaps it's not entirely true. You need to have exactly odd number of points inside the sides. So there is some constraint on that. For example, in this diagram, we have 3 points, which is an odd number. You may also have 1 point inside the side, in which case the configuration looks like this. As you could see, the CVNs concur. But this would rather stray from our actual argument. Let's get back to our idea of isogonal conjugates. There are lines passing through a vertex of the triangle which can be called as isogonal lines. So consider this triangle ABC and we need to take 2 lines through a vertex. Let's take through A for now. So that has to pass through A and intersect. Of course, it will intersect the opposite side at, let's say, the points D and. We call the lines AD and AE isogonal if the angle made by them with the sides AB and AC are respectively equal. They are not lines that make equal angles with the same sides, but rather in opposite order. So you need to consider the angle of the line AD with AB and the line AE with AC. But you can also consider AD with AC and AE with AB. That will also be equal. Then we may call these 2 lines AD and AE as isogonal lines through the vertex A. So this is equivalent to define as reflections about angle bisector of A. That is, if you consider the angle bisector at the vertex, let's use blue colored line to represent this, then clearly then the angle made by the angle bisector with the line AD would be A by 2 minus theta and AE will also be A by 2 minus theta. Hence, they are considered as reflections about angle bisector. This is an equivalent definition. Alright, let's now get to some ratio argument of the points D and E which divides the segment BC. So let me take the same diagram and let us think about the ratios of division by D and D. Notice that if angle made by AD with AB is theta, then the remaining angle would be A minus theta, which is made with AC. Let's call it as alpha for the sake of easier notation. Then the angle made by AE with AB will also be A minus theta. So thus it is also alpha. And that's why I was mentioning that angle made by isogonal lines with opposite sides are equal. You may as well consider in the different order, but you have to consider different sides for those two lines. All right. Now let's look into some area ratios. First, let's only consider the line AD. In the line AD, it divides the entire area ABC into two triangles. So one is the triangle ABD. So we consider the area of ABD to be half times AB times AD times sine theta. For people who are new to this formula, please look into this formula of a triangle, which is half times product of two sides, any two sides, multiplied by sine value of the angle between them. And the area of ACD would be half of AC times AD times sine alpha. Now, hence, this simplifies to AB sine theta by AC sine alpha. So, we get that area of ABD by area of ACD is AB sine theta by AC sine alpha. But if we represent the area in terms of half into base into height formula, we know that the heights are equal and they are going to get cancelled in the ratio because it is common height for both triangles. Hence, it is the base ratio of these two triangles, which is BD upon CD. And let's go to the angle made by AE with the sides. So, by a similar logic, we would get that BE upon CE, that is area ratio of ABE upon ACE, equals AB sine alpha by AC sine theta. Now, alpha and theta are actually some weird variable which depends on the line you choose with. So we need to get rid of it, and that's possible when you multiply these two equations. You would get BD upon CD times BE upon CE equals AB by AC the whole square. And this is going to be an important formula or derivation for isogonal lines. This will prove that those two lines are isogonal. Now, let us discuss about isogonal conjugates. So this is going to be really simple. So these isogonal conjugates are 2 points which are related by isogonal lines. So how are they related is what we are going to do now. Consider a line from A and from B and from such that those three lines concur. Now, let us also consider isogonal lines of these lines from that corresponding vertex. It turns out that these three lines, which are corresponding isogonals of the previous three lines, will also concur, and this point is called as isogonal conjugate of the previous point of concurrency. So the point of concurrency of red, let's call it as R, and blue, let's call it as S. Then R and S are isogonal conjugates of each other. Because if you consider isogonal lines of those three blue lines, then you will get back the three red lines. So you might be pondering why the isogonal lines should... And this is a direct consequence of Ceva's theorem applied along with the equation that we have proved for isogonal lines, the ratio of division of isogonal lines. So let's consider the point of intersection of these three CVNs corresponding to red color as E, D and this implies we can actually define the point of intersection of the blue lines from the formula that we had derived here, this one. So for this, consider D prime, E prime, F prime as the points, and we will be using the above formula to determine these locations, and we will use Ceva's theorem to prove that AD prime, we are going to prove that AD prime, BE prime and CF prime concur. And this proves the existence of isogonal conjugates. So consider BD by CD times BD prime by CD. This is equal to AB by the whole square. This is what we had derived. And if you apply a similar logic from the B vertex of the triangle, then it turns out that CE by AE times CE prime by AE prime equal to BC by AB the whole square. This is just an analogous equation of what we did before, and a similar approach from the vertex C of the triangle would give us AF upon BF times AF prime upon BF prime equals AC by BC the whole square. So we got 3 equations. Let's multiply all of them. So if you multiply all of them and group together the primes separately and the normal letters separately, then you would get BD by C times CE by AF by BF whole multiplied with the primes. BD prime by CD prime times CE prime by AE prime times AF prime by BF prime. Now you would be astonished with how the RHS simplifies. This is so elegant to see that you get AB squared by AC squared times BC squared by AB squared times AC squared by BC squared. And all these terms get cancelled with each other and it results in 1. And let's think about the LHS ones. We deliberately constructed those CVNs through the point R. So hence, this value must be 1 by the Ceva's theorem, isn't it? Let's go back to the diagram. You may see that the red line was intentionally constructed in such a way that they all meet at the point R. So hence, by Ceva's theorem, those ratios BD by CD times CE by AE times AF by BF would be 1. And we are actually going to prove that their isogonal lines will also concur. So that is unknown. So we cannot assume that, though it is diagrammatically true. So since this is 1, the ratio that remains will also be 1. BD prime by CD prime times CE prime by AE prime times AF prime by BF prime is also. And since this ratio is 1, we get that the CVNs corresponding to D prime, E prime and F prime on BC, AC and AB respectively must concur at a point by the converse of Ceva's theorem. Ceva's theorem states that if they concur, then you have the ratios multiplied to 1. And if the ratios multiplied to 1, they all concur is the converse. And hence, the existence of isogonal conjugate is proved. So as a homework, try to think about the isogonal conjugate of orthocenter of a triangle. What is orthocenter of a triangle? Orthocenter is the intersection of altitudes of triangle ABC. Is the orthocenter usually represented by the letter H. So try to find the isogonal conjugate of orthocenter. It turns out to be also a nice point in the triangle. And comment your ideas. We will meet in the next video. Happy learning. Bye.